This paper, List-decodability with large radius for Reed-Solomon codes, is joint work with Asaf, Ferber, and Matthew Kwan. As many of you may know, Reed-Solomon codes are an intensively studied family of error-correcting codes, and we can define them as follows. So first, we need to specify a prime power q, and the code is then going to be over the finite field fq. We also need to specify integers k strictly smaller than n. And then, having specified n, we'll take n distinct elements of this field fq, these elements alpha 1 to alpha n, and these are called the evaluation parents of the Reed-Solomon code. And so we can now define a so-called nk Reed-Solomon code with these evaluation points alpha 1 to alpha n, and that's defined to be the set of code words of the following form. So it's a subset of fq to the n, and it's a set of all n tuples of elements of q of the form f of alpha 1 and so on to f of alpha n, where f is a polynomial over fq of degree strictly smaller than k. So for each polynomial of degree strictly smaller than k, we're going to evaluate this polynomial f at these points alpha 1 to alpha n, and then for each of these polynomials, we get such an n tuple of these evaluations, and these kind of n tuples of these evaluations of these values of this polynomial, these are our sets of code words. So for each polynomial, we get a code word. And so as you can see, this is going to be a linear code over the alphabet fq of dimension k, right? Because that's the dimension of the space of polynomials we are choosing here. So this code has rate k over n, and one can also check that the distance of this code is n minus k plus 1. And so here we have a very good trade-off between this distance n minus k plus 1 and this rate k over n. And in fact, this trade-off between rate and distance is optimal by the single pound. In other words, Reed-Solomon codes are best possible for the so-called unique decoding problem. An important generalization of the unique decoding problem that many of you probably also know is the problem of list decoding. So let me formally define what list decoding means. For some radius in the interval 0, 1, so it's a relative radius in the interval 0, 1, and some list size L, which is an integer, we say that the code in fq to the n is called RL list decodable if every Hamming ball of radius Rn contains at most L code words of this code. So in other words, this code is called RL list decodable if for every point beta in fq to the n, there are at most L code words in this Hamming ball of radius Rn around beta. So in other words, if there are at most L code words gamma, where gamma differs from beta in at most Rn positions, where gamma is in this Hamming ball of radius Rn around beta. So basically, while for the unique decoding problem, which corresponds to the case L equals 1, in every Hamming ball, you want at most one code word. For list decoding, you allow kind of L code words in each Hamming ball. So that means from the noisy signal, you can't necessarily uniquely reconstruct the original code word anymore, but you have a short list of candidates. So or a list of only at most L candidates what the original code word was. And so for unique decoding, this problem of having only at most one code word in every Hamming ball, that directly translates to the code having distance. There's a direct translation between the distance of the code and kind of this sort of radius here you can take. For the list decoding problem, everything becomes a little bit more subtle though, and you can't just kind of get these read off these list decoding properties just from the trade-off between, just from the distance of the code. So, and in fact, as we just said, Reed-Solomon codes are optimal with respect to unique decoding, so respect to kind of list decoding in the case L equals 1, but for larger L, the problem becomes much more complex and much more difficult. And so in fact, even though both Reed-Solomon codes and the notion of list decoding have been intensively studied for more than 50 years, the actual properties of Reed-Solomon codes with respect to list decoding are still not known. So in other words, the best possible trade-off between the radius r, the list size L, and the rate k over n for when list decoding reads Sauermann codes is still not known. Recently, or relatively recently, Kwan and Tamo posed a conjecture for this best possible trade-off between radius, list size, and rate of a read Sauermann code. So their conjecture says that for fixed list size L at least 2 and radius strictly smaller than L over L plus 1, if n is large, then the maximum possible rate of an RL list decodable read Sauermann code is 1 minus L plus 1 over L times R. So basically, for given rate and list size, you want to optimize the rate of the code, make the code as big as possible, and they conjecture that the maximum possible rate is given by this term. They showed that this term is in fact an upper bound for the rate that follows from a fairly simple counting argument. And more interestingly, they proved that this rate can be achieved if the list size is L is either 2 or 3. So in this work, we prove that for larger L, this rate can be achieved at least up to a constant factor. So one way to phrase our results is to say that in the setting of this conjecture of Kwan and Tamo up here, one can achieve a rate which is a tenth of this term. So we can achieve rate 1 over 10 times 1 minus L plus 1 over L times R. So in general, the conjecture is still open, but we show that it's, so Kwan and Tamo showed that this is always an upper bound, and we showed that there is a lower bound, so this can be achieved up to a constant factor. Okay, but because of the constant factor loss, this is kind of this is kind of most interesting in the case where the radius is very large. So, so for the rest of the talk, I'm going to focus on the case of large radius. So more precisely of radius tending to 1. So from now on, let us consider these problems in the setting where the radius r for our list decoding is of the form 1 minus epsilon for epsilon tending to 0. And in this setting, by the list decoding capacity theorem, one can deduce that every 1 minus epsilon L list decodable code, so every list decodable code where the radius is of this form, has rate at most 1 plus L of 1 times epsilon, unless the list size is exponential in n. So unless the list size is unreasonably large, the rate is upper bounded asymptotically by epsilon. And so this kind of observation caused Guo, Li, Kwan, Tamo, and Wouters to ask in the talk that was just preceding this talk here, whether this rate, the rate of this form can actually be achieved at least in order of magnitude. So they asked the question, do there exist 1 minus epsilon L list decodable read Sauermann codes of rate omega of epsilon and list size L exponential in n? So can you achieve a rate of order epsilon when list decoding with a radius of 1 minus epsilon and list size L less than exponential in n? And so in this paper where they kind of had this as their main motivating question, they proved that you can achieve this rate up to log factor. So they proved that there are 1 minus epsilon L list decodable read Sauermann codes with list size L being on the order of 1 over epsilon and rate being epsilon divided by a logarithmic term. And so that result improved upon the lower bound epsilon squared for the rate that one obtains one obtains from the Johnson bound. So by the Johnson bound, one can more or less automatically see that there are Sauermann codes of this rate epsilon squared, but they improved it to epsilon over a log term. And so, but their main question, the main motivating question as they wrote in the paper was to ask whether you can get rate omega of epsilon. And so we answer this question affirmatively and show that there exists 1 minus epsilon, 3 over epsilon list decodable read Sauermann codes with rate at least epsilon over 15. So you can take list size still, order 1 over epsilon, in fact 3 over epsilon, and get rate epsilon over 15. And so the constants here are actually not optimized. Our proof is very short, just 4 pages. And so we to keep things simple, we kind of didn't optimize the constant. But if one goes through the argument carefully, the denominator of 15 here for the rate can be improved to any number larger than 2 at the expense of increasing this constant 3 here in the list size. And so that was also observed later by Goldberg, Kwan, and Tamo. Okay, so here's again our result. So we prove that there are list decodable Sauermann codes of this rate epsilon over 15 when you have the list decoding radius 1 minus epsilon and list size 3 over epsilon. And I want to point out that, so this result relies on the field being large. However, it doesn't have to be as large as in the previous results on this topic. So in particular, the preceding result of Gurley, Zhangguan, Tamo, and Wouters required the field size Q to be exponential n, whereas we only needed to be polynomial. So we only need for this result Q to be, this field size Q to be at least n to the 1.25. And in fact, we can make the field size almost linear in n. So here, for the result as stated here, we need Q to be at least n to the 1.25. But at the expense of increasing the various constants in the statement, we can make the field almost linear. So for every fixed constant C at least 5, it suffices to just assume that the field is of size n to the C over C minus 1. So if you take C very large, it's basically close to linear. And then you can get a similar result where you kind of lose on this constant 15 here. So this 15 becomes 3C. So this result corresponds to taking C equals 5 in this more general theorem. But so the point of this is that you can make the polynomial better that you require for the field size. Okay, so here's again our theorem. So we show that for every fixed constant C, one gets these nicely list decodable Reed-Solomon codes with rate linear and epsilon, list decoding radius 1 minus epsilon, list size 3 over epsilon, and the field has to be sufficiently large, but only polynomially large. And in fact, you can take the exponent of the polynomial arbitrarily close to 1. As in previous works on this problem, our proof shows that that with high probability, a random choice of the evaluation points for the Reed-Solomon code gives the desired list decodability properties, but we don't actually get an explicit construction of such Reed-Solomon codes. So that's also this. That approach is very similar to previous works on this topic. And one other thing I want to mention is that we did use this theorem up here actually from a more general result concerning list decodability of random puncturings of any given code with very large distance. So the polynomial structure of these Reed-Solomon codes is actually not really used. It's just, you can generalize this to codes of very large distance. So this is a little technical to state, so I won't tell you the details, but roughly speaking, our more general result says that for a code with block length m and distance m minus h for some small h, so with very large distance, then if you take a random puncturing with block length n's, and so that corresponds to taking these evaluation points here randomly, you likely, for this random puncturing, get a list decodable code with a radius 1 minus O of h over n and list size n over h, if you assume that the alphabet is large enough and that n is not too big. But if you care about the details, they are in our paper. And so just at the end, I want to comment on some works that appeared after our theorem. So here's again our the simple version of our statement, having radius 1 minus epsilon, list size 3 over epsilon, having these list decodable codes with rate at least epsilon over 15. And as I said, the 15 here is not optimized. You can get any number larger than T2 at the expense of increasing this 3. And so then this result was then improved by Goldberg, Zhangguan, and Tamo, who improved this rate we had here to any rate approaching epsilon over 2 minus epsilon. So remember here we can get epsilon divided by any constant bigger than 2, and so they improved that to 2 minus epsilon. And then the list size L depends only on the gap between the rate and epsilon over 2 minus epsilon. And that was again improved by Guruswani and Moshev, who showed that there are 1 minus epsilon L list decodable Reed-Solomon codes with rate approaching epsilon. Here, however, the list size L depends exponentially on the gap between the rate and epsilon. And so in particular, while here the trade-off between the radius and the rate is basically optimal. So remember that there's a this basically matches the upper bound from the list decoding capacity theorem. However, the list size L is much worse in their result. So in that sense, it does not completely subsume those results. And also the field size is going to be larger in this very recent result of Kuduswamy and Moshe. Okay, that's all, and thank you very much for your attention.